Hello and welcome to this video for basic sentential logic, informal fallacies, and cognitive biases. In this video, I'll be talking about material that corresponds mostly to section 2.8 of the book, and in particular, the topics are going to be relations between statements. So, in the previous video, we looked at different categories that a single statement might fall into. It could be a tautology, a contradiction, or a contingency. In this video, we'll be looking at some relations that may or may not hold between two statements or a set of statements larger than two, 3 or 4 statements. And those relations will be consistency, equivalence, and implication. So I'm going to first start off by looking at all 3 of these relations just in the case of 2 statements. Are 2 statements equivalent? Are 2 statements consistent? Does one statement imply a second statement? And then after we are comfortable doing it with 2 statements, we will see how to generalize the same relations to 3 or more statements. And this is going to help us to understand logical relations in a lot of ways, just like knowing whether a single statement is a tautology, contradiction, or contingency. Knowing what kinds of logical relations can hold between 2 statements will help us out. So the first relation is equivalence. And here's the definition. 2 statements are equivalent if they have identical truth columns. So to test for equivalence, you construct a joint truth table. That's just one truth table that has both of those statements on it. And you compare their truth columns. Okay, the columns of T's and F's underneath the statement. And if those columns are identical, they're exactly the same. It's the same pattern of T's and F's down on both columns, then those statements are equivalent. If there's any row where they have a different truth value, then they're not equivalent. Consistency. 2 statements are consistent if and only if it's possible for them to be true at the same time. And to test for this, again, you do a joint truth table that has both statements on it. And now you're just looking for any row where they're both true. And if there is such a row, then those statements are consistent. If there's no row where they're both true, then they're inconsistent. The final relation is implication. And this one's a little more complicated to state because implications are directional. So if you have 2 statements, alpha and beta, one question is whether alpha implies beta, but it's a separate question whether beta implies alpha. With consistency and equivalence, there's no directionality. If alpha and beta are equivalent, then alpha is equivalent to beta, beta is equivalent to alpha. And same thing with consistency. But with implication, there is a directionality to it. That makes it a little more complicated to state. But here's what it means. Statement alpha implies statement beta if and only if. If alpha is true, then beta must be true. So here's the test. To see if alpha implies beta, you do a joint truth table that has both of those statements on it. Then you're going to look for a row, any row, where alpha is true and beta is false. You're going to look for that combination. We're going to call that a counterexample row. Okay, so you're going to look for a counterexample row. If there is a counterexample row, then that implication does not hold. Alpha doesn't imply beta. But if there is not a counterexample row, then the implication does hold. Alpha does imply beta. So I just gave you 3 definitions and 3 tests. It might sound like a lot, but after we work through a few examples, you'll see that it's actually pretty straightforward. So here's the way it works for 2 statements. I'll give you 2 statements like this, statement 1, statement 2, and say, do a truth table for these statements and answer the questions. Are they equivalent? Are they consistent? Does statement 1 imply statement 2? Does statement 2 imply statement 1? So that's what the questions will be like. Step 1, as always, is just to do a joint truth table. So it's a truth table that has both of those statements on it. And this is what it would look like. Got P and Q. We built up all of our components here, not P, not Q, conjunction P and Q, the negation of the conjunction, and then the conjunction of the negated atomic statements. So hopefully at this point, you're comfortable constructing truth tables. Now that the truth table is there, we can answer the questions. So are 1 and 2 equivalent? So here's statement 1. This is column 6, and here's statement 2 in column 7. So we're going to be comparing these truth columns, right? Remember, they're only equivalent if the entire truth columns for both statements is exactly the same. So what we're doing is we're essentially looking for any difference between them. And here on row 3 that I've just highlighted in green, you can see that there's a difference. And it only takes one. Once you find a difference, you can stop looking. You know they're not equivalent. So the statements have different truth values on 1 or more rows. Example, row 3. So they're not equivalent. That's how you would answer that question, because if it's not multiple choice, you'll need to explain your answer. So if the question is, are 1 and 2 equivalent? The answer would be the statements have different truth values on 1 or more rows, so they are not equivalent. Are they consistent? Well, now what you're doing is you're just going to go down and look for any row where they're both true. And it only takes one. Now, there could be more than one, but as long as there's at least one row where they're both true, then those statements are consistent. And you can see here in row 4, both of those statements are true. So because there is at least one row where both statements are true, they are consistent. And I've indicated the row where they're both true, row 4. So that's how you would answer that question. Next up, does statement 1 imply statement 2? So what we're going to do is, for implication questions, we're going to look for a counterexample row. And what a counterexample row is going to be is a row where this one's true, but this one's false. So if I ask, does 1 imply 2, I need to look for a row where 1 is true, but 2 is false. This is statement 1, this is statement 2. So I'm just looking for any row where 1's true and 2 is false. And you can see right here on row 2. So as soon as you find a counterexample row, you can stop looking. You know that the implication doesn't hold. Now, it turns out there's also another row that has a counterexample row. So there's more than one. But it only takes one row to show you that the implication doesn't hold. So I can just stop here and say there is at least one counterexample row, row 2, where 1 is true and 2 is false. So 1 does not imply 2. Okay. Well, the question I just asked and answered was, does 1 imply 2? But there's a different question, which is, does 2 imply 1? Remember, there's a directionality to implication questions. And that's a different question. Even though 1 does not imply 2, it could be the case that 2 implies 1. Let's see. So I can ask, does 2 imply 1? I'm still going to look for a counterexample row. But this time my counterexample row is going to be where 2 is true, but 1 is false. Okay, so where I have a T here, but an F here. Is there any such row? And if you look down, you can see there isn't any. There's no row where statement 2 is true, but statement 1 is false on that same row. So there's no counterexample rows. That is, no rows where 2 is true and 1 is false. So 2 does imply 1. So that's the idea behind how these sorts of questions will work. You'll be given a set of statements. Right now we're only working with 2, but in a minute we'll generalize to 3 or more. You're given a set of statements. You'll do a truth table that has all of those statements on it. And then you just answer those relation questions given the definitions. Let's do another example. Here my two statements are if A then B, and if not B then not A. Question 1, are 1 and 2 consistent? For consistency, remember, you're looking for any row where they're both true. And yep, row 1. It only takes one row for them to be consistent. So as soon as you find one row, you can stop looking. There are more, 3 and 4. They're both true, but I've got what I need to answer the question. There is at least one row, for example, row 1, where 1 and 2 are both true, so they are consistent. Next up, are they equivalent? So now I'm looking for any row where they're different. Okay. And there isn't any row. These truth columns are identical. They have the same truth value on every row. So it turns out they are equivalent. Their truth columns are identical. Next up, we have the implication questions. Does 1 imply 2? Does 2 imply 1? So with 1, does 1 imply 2? I'm looking for a counterexample row where 1 is true but 2 is false. And you can see there's no counterexample row here. There's no row where 1 is true but 2 is false on that same row. So there's no counterexample row, so that implication does hold. 1 does imply 2. Does 2 imply 1? Well, now I'm looking for a counterexample row where 2 is true but 1 is false. And again, you can see there's no counterexample row at all. So that implication also holds. 2 does imply 1. Okay, so we've got the definitions of these relations for two statements. Walk through a few examples. Hopefully it's pretty straightforward now. Let's generalize this to 3 or more statements. And the generalization is actually pretty straightforward. So for equivalence, if you have a set of statements, it could be 3 or 5 or 20. Those statements are all equivalent if they all have identical truth columns. So you do the same thing. You just make a joint truth table that has all of those statements on it. And if all of those truth columns are exactly the same, then those statements are all equivalent. If there's any difference anywhere, even if you have 20 statements, if there's just one statement that has one different truth value from the others on any row, then those statements are not all equivalent. So in order for them to all be equivalent, they have to have identical truth columns. For consistency, a set of statements is consistent if there's at least one row in which they're all true. So it's this, again, it's the same test. It's just instead of looking at 2 rows, you're looking at however many rows you have for all of your statements. And if there's a row where they're all true, then that set of statements is consistent. What about implication? Or sometimes we'll call it joint implication, just to highlight the fact that we're talking about multiple statements and whether or not they imply some other statement. Well, this is also tricky because of this directionality in implication. And the way we're going to handle that directionality is that when we have a larger set of statements, we're going to ask the question in this way. Does a set of statements here A1 through AN, and N could be anything, N could be 2 or 20 or whatever, but we've got some set of statements here, the alphas. Do they jointly imply some single statement B? That'll be the way the question works. And you'll see examples in a minute. And the definition is that this set of statements, alpha 1 through alpha n, do jointly imply beta if and only if all of these are true, then beta must be true. And the test is essentially the same as the test for two statements. You construct a joint truth table that has all of those statements on it. You look for a counterexample row. In this case, it's going to be any row where all of these are true but beta is false. That's what you're looking for. If there isn't a row, if there's no counterexample row like that, or I'm sorry, if there is, suppose you do find it, if there is a counterexample row, then the implication doesn't hold. A1 through AN don't jointly imply beta. If there is no counterexample row, then alpha 1 through alpha n do jointly imply beta. So it's essentially the same test. It's just the counterexample row you're looking for is a little bigger because there's more columns involved. Once you see a couple of examples, you'll realize how easy it is. So it'll look like this. Here's 3 statements, and you'll be asked questions. Are they equivalent? Are they consistent? And then some implication questions, some joint implication questions. So step 1 is to get the joint truth table up and running here. Here's statement 1, statement 2, statement 3. I'm going to just put numbers up here to help me keep track. You can do that also if you want. Question, are 1 through 3 equivalent? Well, in order for them to be equivalent, they have to all have identical truth columns. True, false, true, 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 false, true, 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 false, true, true. Looks like they're all exactly the same. There's no row where they differ. All true, all false, all true, all true. So it turns out those are all equivalent, which is interesting. If you just first looked at these, you might not realize that they all are logically equivalent. They all mean the same thing, even though they're stating it in a different way. But yes, they are all equivalent. Are they consistent? Well, now we're just looking for any row where they're all true. And row 1. Yeah, there's more rows where they're all true, but it doesn't matter. As soon as you find one row where they're all true, you've got everything you need to answer that question. In this case, answer it with yes. Okay. Do 1 and 2 jointly imply 3? So here, I'm going to be looking for a counterexample row where 1 and 2 are both true, but 3 is false. Okay. Is there any counterexample row where these are all true, but that's false? Where 1 and 2 are true, but 3 is false? No, there isn't. So there's no counterexample row, so that implication does hold. 1 and 2 do jointly imply 3. Let's do another example. Now we have 4 statements. Here's the joint truth table. And I've got, I'm going to put numbers up here. This is statement 1, 2, 3, and 4 is just B, so 4 is here. Equivalence question. Are 1 through 4 equivalent? Now remember, in order to be equivalent, they all have to have exactly the same truth value on every row. Okay. Okay, so you just look and see if the truth columns are identical. Or another way of stating it, look and see if there's any difference anywhere. And look, I've sort of outlined, so this is 1, 2, 3, 4. I've just put a green box around those statements on row 3. You can see there's a difference. These are false, but statement 3 is true. It only takes one row where there's one difference in truth value and to sort of ruin the equivalence. So we looked, and there is at least one row, row 3, where the statements don't all have the same truth value. So they're not equivalent. Those truth columns are not all identical. Are statements 1 through 4 consistent? Now we're just looking for any row where they're all true. And that's going to be quick, row 1. It's quick if you were looking from the top down anyway, I guess. Because row 1, 1, 2, 3, and 4 are all true. So yes, 1 through 4 are consistent. There is at least one row, row 1, where they're all true, so the statements are consistent. Now let's ask some implication questions. And with a set of 4 statements, there's a bunch of implication questions you could ask. I could ask, do 1 through 3 jointly imply 4? Do 2 through 4 jointly imply 1? Do 1, 3, and 4 jointly imply 2? Right? So you can see there's a lot of different implication questions you might ask. I'm just going to go ask 2 of them in this case. So first, do 1 through 3 jointly imply 4? And as always, all we're doing is looking for a counterexample row where 1 through 3 are true but 4 is false. So I'm looking for any row where these are all true but 4 is false. So where these are all true but 4 is false. Is there any row like that? Nope. If you look down here, there's no row where these are all true, but that's false. So there's no counterexample row. So that means the implication holds. 1 through 3 do jointly imply 4. Let's ask a different question. Do 1, 2, and 4 jointly imply 3? Still, we're going to look for a counterexample row where this time the counterexample row would be where 1, 2, and 4 are true, but 3 is false, right? Where these are all true, but that's false. So where 1, 2, and 4 are true, but 3 is false. Is there any such row? Yeah, right here on row 6. 1, 2, and 4 are all true, but 3 is false on row 6. So there is a counterexample row where those are all true, but 3 is false. So the implication does not hold. 1, 2, and 4 do not jointly imply 3. Okay, so that's the end of the video here. Hopefully at this point what you can do is you can construct a truth table for any statement or any set of statements. You can answer questions for a single statement, whether any single statement is a tautology, contradiction, contingency. And you can also answer relationship questions about sets of statements. Is a set of statements, are they equivalent? Are they consistent? And does some statement or set of statements imply some other statement? Next up, we'll be applying these results to assessing argument validity.